Hey peers, it's Mrs. Coleman here to talk to you about electrochemistry. Now, some of you when you're little may have done this awesome experiment with a lemon and an iron nail and a copper penny, and you may have attached wires to it and a little light bulb or maybe a voltmeter, and you could actually see that electricity was running or flowing through this lemon. Now, what this basically is a redox reaction, and it's the basis of all electrochemistry. So remember, electrochemistry is all about moving electrons in a reaction, which is a basic redox reaction. So we've got our species A here, and it's going to lose electrons, transferring it to species B, which is going to gain electrons. And so we say that species A has been oxidized as it loses electrons, and species B is reduced as it gains electrons. Now, if we take a look at a very simple redox reaction, the redox reaction between zinc and copper, we can see even more things. So if I take a piece of zinc, for example, and I put it in a solution of copper ions, what you'll notice over time is that a single replacement reaction happens. Copper starts to form on the outside of the zinc as the zinc loses electrons, and the electrons from zinc, the zinc is actually turned into zinc ions in the solution. And so if I take a look at this redox reaction, I can break it up into its half reactions. The zinc is being oxidized as it loses 2 electrons, and the copper is being reduced as it gains 2 electrons. And I can actually measure the potential energy of these two different half reactions in volts. We can see that the standard reduction potential of our oxidation reaction is 0.76 volts, whereas the standard reduction potential for our reduction reaction is 0.34 volts. And now those are going to come into play in just a little bit. So when I put this piece of zinc in this copper solution, I'm going to get the redox reaction to happen, the single replacement reaction, but nothing else is really going to occur. Let's see what happens when I actually separate the two half reactions in two different beakers. If I place the zinc piece of metal in a solution of zinc ions and a piece of copper metal in a solution of copper ions, and I connect them with a wire, what I'm actually going to see is a flow of electrons from the zinc as it loses electrons, and those electrons are going to flow into the copper. Now, as soon as that happens, the flow is going to stop because they haven't completed the circuit. But if I add a salt bridge, which is basically like a gel or a liquid of a salt, in this case sodium nitrate, I've actually completed the circuit, and we're going to see those electrons continuing to flow from the zinc to the copper. And if I take a look again at those half reactions and I look at those reduction potentials, I can actually figure out how much potential energy is flowing from one side to the other. And I can do that because I can add up the reduction potentials of each of the half reactions. And when I do that, I can see that 1.1 volts are traveling from one side to the other. And again, I just added those reduction potentials of the half reaction to get the overall cell reduction potential. So this is actually called a galvanic cell or a voltaic cell, depending on where you're reading it from. So a galvanic cell is made up of an anode and a cathode. And an anode is where the oxidation half reaction is going to occur. We place it in a reducing agent. The cathode is where the reduction reaction is going to occur, and we place it in an oxidizing agent. We always have to have the salt bridge to complete the circuit, and the flow of electrons is going to go from the anode to the cathode. As the anode loses electrons, the cathode is going to gain them. So what we can see, what will also happen is that because we have the flow of electrons from the anode to the cathode, as I lose electrons here and gain them here, we're actually going to change the mass of these pieces of metal. The anode is actually going to reduce its mass because these metal atoms are turning into metal ions in solution. Whereas here, the ions in solution are going to be gaining those electrons and becoming the solid metal, adding to the cathode. So we're going to see the cathode increase in mass and the anode is going to decrease in mass. So let's do an example problem. So if I take a reaction between iron 3 and copper, we're going to get a redox reaction to form iron 2 and copper 2. So here are the important half reactions. So I can see that iron is going to go from +3 to +2, and copper is going to go from a charge of 0 to a charge of +2. And so I can actually look up those reduction potentials in a standard reduction potential table. Now, AP is going to either provide you with a table that looks like this, or they'll provide you with a smaller table with just the important pieces of information. So if I take a look at these half reactions, I can add them up to get my overall full reaction. But as you can see, I don't have the right things to add. So I have to do a couple of things. The first thing I need to do is reverse this reaction here. So if I reverse that reaction so that it fits the process, what you'll notice is that I also had to change the sign on the reduction potential. So I reversed the reaction here, I had to reverse the sign here. Now, we can also see that I've got 2 electrons here and only 1 electron here. So I need to double that top reaction. So I've got 2 electrons and 2 electrons. The electrons have to balance. If I double the electrons, I double everything else. Now notice, I doubled the coefficients, but my reduction potential did not change. Remember, reduction potential is just a measure of the likelihood of electrons to flow or species to be reduced. The amount of substance doesn't make a difference. So now I'm ready to add up my 2 half reactions to get my overall reaction. And again, I'm just adding those reduction potentials to get the overall reduction potential of the entire cell. I hope you found this helpful. Stay tuned for the other videos about electrochemistry. See you later.